Good evening.
Good evening.
Our speaker is here tonight to give us an update on the horrific events at the Fukushima nuclear power plants in Japan last year. What happened and its health and economic consequences. Dave Bockstans is a member of the Tea Party of the Lehigh Valley and on the Energy and Environment Committee. Since 1981, Dave has been involved in the design and operation of PP&L Susquehanna Steam Electric Station, a 2-unit boiling water type nuclear power plant located near Berwick, PA. Dave's career has been devoted to the safe and reliable operation of all nuclear power plants and the Susquehanna plants in particular. For most of this past month, Dave has been working directly over the open Susquehanna reactor vessel, that's why he's glowing tonight, while the plant operators swapped old fuel for new and inspectors examined the vessel internals. The Susquehanna plant design is a very similar one to the Fukushima nuclear plants, which gives Dave a unique perspective on the events that occurred there following the devastating earthquake and tsunami that caused so much damage and loss of life in Japan in the spring of 2011. Tonight we'll explore just what happened at the Fukushima plants last year. Just as importantly, we'll also hear about what didn't happen that might surprise you. Please take good notes, prepare your questions for the Q&A session at the end. While Dave is an employee of PPL, he is here on his own and is not speaking for the company. So please, no questions about your electric bill or the blackout that caused all your milk to spoil last Halloween. Please join me in welcoming Dave Bockstans.
Thank you. Yeah, I'm not really glowing right now, but I really don't.
He's not pregnant either.
This is a genuine rush time. But I don't really need a night light when I go to the bathroom at night. Hold on just a second. Here. Buried my stuff. Okay. Something I found while doing some research here has absolutely nothing to do with this, but it's a good parable about kind of why we're here. Anybody here ever hear of the red cockaded woodpecker? All right, it's my favorite woodpecker. There's a recovery plan for the red cockaded woodpecker sponsored by the U.S. Fish and Wildlife Service. Okay. They got a team together of 17 august individuals, several of them on the government payroll and several from academia. But I don't know what drew me to this, but I want to just read a little bit from the acknowledgments. The process of revising the 1985 red cockaded woodpecker recovery plan began in August 1995 when potential recovery team members were identified. The first team meeting was held in March 1996. 2 additional meetings, each 1 week long, were held in April and December 1997. Okay, this is a government project. This is on your dime. Between March 1996 and March 2000, team members individually spent hundreds of hours working on the revision, including participation in team meetings, writing, and reviewing. By April 1999, much of the introduction had been drafted. Your dollars at work, thank you. All right. Yeah, as Paul said, I've got several years of experience at PPL. I'm going to stand over here because I got to watch this with you. I'm interested to see this too. And I'll just zap Paul with the laser here when I want him to advance. Yeah, we're going to be discussing, as Paul said, the Fukushima events of last year and some of the aftermath. So Paul, why don't you go ahead? All right, I'm going to quickly go through some of the boring stuff here, but this is what basically what the Fukushima plant looks like. It's also very similar to the Susquehanna plant, the 2-unit boiling water reactor up near Berwick that I work to support. It's also similar to the Limerick plant. If you go down Route 100, you'll go right past it in Limerick, Pennsylvania. Also on the Delaware Bay, there's the Hope Creek plant. very similar in design to this. We've got the reactor core here sitting inside of a pot that's inside of a thick-walled steel reactor vessel that contains all the water surrounding the core, and it's enclosed inside of a metal and steel containment structure. Okay, so we've got, this is just to illustrate that there are multiple barriers between this thing that's the core, where all the uranium is, and the outside world, which is outside here. Okay, so we've got multiple barriers and multiple ways of getting water into the core here. I'm expecting you all to take good notes, and there's a lot to get through here, so if you can save your questions for later. Okay, Paul? All right, fission is what we live for. Okay, the uranium atom is sitting there minding its own business, perfectly fine. You can pick up a new fuel rod, and you can handle this stuff, and no problem at all. Until along comes a speeding neutron. Okay, you may recall that the atom nucleus consists of neutrons, which are the gray dots, and the red dots here are protons. Okay, so it's all kind of held together in this great big mass of protons and neutrons. The number 235 means there's 235 of them in there. It sucks up one more neutron, becomes uranium-236, and becomes unstable and busts into two smaller products we call daughter products. Called daughter products because they reproduce themselves. They will continue to decay and produce more and more products, but these are the leftover chunks of matter after you get the fission here. Well, the other thing that happens when you have a fission, it's what you call it when an atom breaks apart, is it liberates a couple more neutrons. And if you're not careful, or if you're designing it that way, you can see what happens. One neutron then becomes two neutrons, and two neutrons encounter two uranium atoms, and if you allow that to progress geometrically, you can have quite an interesting result. The way we design our cores, this doesn't happen. Primarily, we keep the concentration of the uranium-235 very low. If the guys in Iran are telling you that what they're doing is for commercial use, ask them what's the concentration of uranium-235 in what they are producing. If they say that it's about 90%, they're not talking about producing power with it. But there's one other thing that happens when this uranium atom breaks apart, and you can think of it like a popcorn ball, and you bust it in two. You get two big chunks and a bunch of small pieces go flying around. But you got these daughter products and a couple of neutrons. Well, when you add up the mass of these, in this case, 4 different pieces, it's actually less than the mass of the uranium-235 atom plus the neutron. What happened to that remaining mass? Okay, who remembers the famous Einstein equation? E equals mc squared. All right, E equals mc squared. That means energy is equal to the mass times the national debt squared. I'm sorry, it's not that big. It's only the speed of light. Mass times the speed of light squared. Okay, so you can see that then a little bit of missing mass turning into energy is a lot of energy. Okay, and we've got lots of these things going on, and it's a sustained reaction. That's where the energy comes from, is from actually we're losing mass. The universe is losing a little bit of mass with every fission that's going on. The complication that all nuclear plants have is that, like I said, these daughter products continue to decay. They're hot. They keep on going. They don't need any more neutrons to decay and give off more heat. So the classic problem that we got with the plants is after you've shut down, you haven't reduced the energy production to zero. Okay, the Susquehanna plants are roughly 1,000 megawatts electric each. It starts off at about 3,000 megawatts thermal of heat. 3,000 megawatts of heat is produced here. When you shut it down, you take an emergency shutdown and the plant is stable, it's shut down, it's still producing 6% power. So 6% of 3,000 megawatts is still a lot of megawatts. So that's a lot of heat that has to be removed. And if we keep the core covered, if we keep water over the core and circulating through it, it's fine. If that gets interrupted, we'll see what happens. Okay, Paul? Okay, this is a fuel pellet. Like I said, you can handle a new fuel pellet. This is a fuel pellet in production. It's all the size that an individual pellet is. It's just a tiny little thing. Okay, on to the next. Then we take these things, we stack them up inside of tubes, and this is a typical fuel bundle for a boiling water reactor. This shows 4 of them here, and one is cut away in this diagram. And each of them has a series of tubes that are all held together in parallel inside the core. And each of these tubes is just a stack of those pellets that we saw a second ago. And in the Susquehanna core, there's 735 of these bundles. And each of the bundles is a 10 by 10 array. Okay, and it's about 14, 15 feet long. So that's how much raw uranium and other stuff is in there in terms of pellets. Okay, so that's what we're dealing with. This is, Paul said, I've spent much of the last month looking down into the reactor. This is what I saw. You're looking down here is the reactor core itself. All right, this is a used fuel bundle, and it's being pulled up and it's being taken out of the core and put into the spent fuel pool for long-term storage. So it's got this beautiful blue glow. That's called a Cherenkov radiation, and that's where you're actually seeing the light given off by one of those neutrons that was shooting out from the core. It's actually slowing down while it's encountering the water that's surrounding it. And when in the action of slowing down, it gives off this beautiful blue glow. So you can see that's not a light down there, that's the actual core itself glowing that way. So when you say it, talk about nuclear glow, that's it. Okay, next. This is a spent fuel pool. Okay, so they pick that bundle up, they haul it over, and then they set it down in this array, this sort of an egg carton kind of thing, maybe more like a beer case, right? And you're just setting it down in there. This whole pool is probably, it's about half the size of this room. If you divide this room in half, this whole thing here would fill us up, and it's all full of water. Okay, next. All right, this is the Fukushima plant in Japan. This is how it was prior to March of last spring. It has 4 units here, 1, 2, 3, and 4 along there, and there's actually 2 more over here, 5 and 6. Okay, so it's right on the coast, and you can see it's got this setup with some breakwaters out there. Okay, next. It is just some of a large number of nuclear plants in Japan. Japan had gone very much for nuclear power. They have no natural resources of their own for which to generate electricity. No oil, no coal, maybe a little geothermal, but not enough to really make much of a difference for them. So they had launched onto a program of building nuclear plants, and they're all around the island. Okay, next. All right, so this is that's where the earthquake occurred. All right, it's the largest earthquake at a Category 9 on the Richter scale, and the color grade, you can see just what areas are most affected. The Fukushima plants are right down in this area, right here. I mean, Couldn't be much closer. All right, so you had a huge earthquake that occurred on this day, and it was devastating to the countryside. Okay, next. All right, so 11 reactors automatically shut down. In Japan, you have an earthquake, boom, down they go, because they expect earthquakes to happen, and they'll have an emergency shutdown. Okay, again, if you take emergency shutdown, you shut down quickly. Do you go to zero in power inside the core? No, you haven't stopped heat production, so you got to keep pulling that heat away from there. There were another 3 that were affected in that area that were already shut down. There were 3 of the Fukushima plants, units 4, 5, and 6, were not operating at the time. They were shut down. I've talked to some of the people that were there at the time. And the earthquake happened, and they got out of the plant, and they had 2 places they could have gone to. One was their hotel, and one was a closer hotel that happened to be up on a hill. They decided to go to the closer hotel. The hotel they were in didn't last very long. Okay, next. All right, so they lost all off-site power. Okay, we're designed to be able to take that. If power to the grid goes away, like it happened here locally last October, we have emergency on-site power. We've got a set of emergency diesel generators, basically a diesel locomotive sitting there ready to produce electric power for you. And they start up right away, and they provide the house loads to the essential things to, again, keep that heat being removed from the core. And they started up just fine, and the plants were shut down and were stable. There was no significant damage. They hadn't actually walked through the plants, but they shut down as expected, and they were stable and operating in a shutdown state. Okay, this is after that huge earthquake. Okay, next. 41 minutes after, the first of 7 tsunamis hit the site. First one was approximately 13 feet, and it was blocked by that seawall that you saw out there. And they can measure that. They have a little tide gauge that they can measure. At least one of the waves arrived at the station was 46 to 49 feet. The only way they knew that was they could see the water level marks on the side of the building, because their instrumentation that measured this 13 feet, gone. Okay, next. They were designed for 18.7 feet. Okay, that's what they were designed and licensed for. This is what it looked like as the tsunami came rolling in. All right, here's some of those buildings that we saw in the overhead shots. Next. All right, here, this might be a little tough to see, but it's a good illustration. You got the ocean out here, the tidal wave comes in. All right, this is where the reactor is. It's called the reactor building, naturally. The reactor produces steam, goes through a turbine, and that's housed in the turbine building. Okay, you can see the water level here that came sloshing up over the shore, and there's a little illustration here. These are doors here. The doors that get you into the plant are underwater. Okay, the height 14 to 15 meters over the ground level. Okay, next. All right, you got to use your imagination, and now you're looking at it from the other direction. Okay, the ocean out here, and now you're looking inside the plant. This is the water level here. Here's that reactor that we saw in the earlier picture. Those emergency diesels that started up and ran just fine, that's the green block right there. They put it in the basement, right up by the shore. Okay, the batteries. Backup power to the diesels, the batteries, put them in the basement. Okay, the control room where the operators are up here. Well, what do you think happened to the diesels? You also have these yellow blocks are switch gear, which is the stuff you need to have to think of it like a fuse box, or you know, it's what gets the power to where it's supposed to go. All that underwater. kaput. All right, so those waves come in and they knock it off. All your off-site power was already gone, and now you lost your on-site power. All right, so let's see what happens. Okay, so this was the state we were in. Again, we had some makeup water being driven from those diesels, from power from those diesels, and you had water in here. You also have water in these things, which is called a pressure suppression pool. It's kind of like a donut shaped, full of water, and if steam gets released out of the vessel here, it gets directed down in here and it condenses, okay? So, you know, if you blow steam into water, that the water is going to cool off the steam and it's going to condense, and it keeps the pressure down inside of this, which is kind of like an upside down light bulb. Not a curly fry light bulb, but one of the classic light bulbs. All right, and up here is the spent fuel pool. All right, that's what is up there that we saw the picture of. Okay, so tsunami comes, you lose the diesels, and now all of a sudden you have no makeup coming in here. All right, and how much power is being produced in there? Roughly 6% of the original. Okay, so we're getting hot, and this is all bottled up. Okay, so if you got heat in a bottled up enclosure, pressure starts going up. All right, so we got to deal with that. There was a system that can operate off of the batteries that actually takes steam off of the top of the core, and there is steam being produced. It drives its own little turbine and drives a little pump, and it kind of circulates around in here. So it has a self-contained system, and that was fine as long as you have batteries. Okay. Well, as we saw, the batteries didn't last very long. All right. So here we are back to hot core and nothing coming in. All right. So what happens here? Well, you start building up pressure. You've got to get rid of that pressure. So they open up a what do you call a relief valve, and it directs steam down into the suppression pool. This big donut down there that's half full of water, and they're just coping now. Okay, so they're directing the steam down in here, right? And we're losing inventory because steam is coming up, no water is coming back in. All right, so now we're down to the top of fuel. All right, we keep on going, and what do you suppose is going to start happening to that fuel?
Get hot, melt.
All right, starts getting hot. All right, now there's one thing I mentioned about those little fuel pellets. They're inside of a tube. That tube is a zircon alloy that is just great for producing power, and as long as it stays cool, we're great. But when it starts getting really hot, when it gets uncovered, the water that comes in contact with it will actually burn. It takes the oxygen out of the water, H2O, takes the oxygen out of the water and forms a zirconium oxide layer. And what happens when you take the oxygen away from the water? What do you get?
Hydrogen.
Hydrogen. Start producing hydrogen. Hydrogen starts accumulating in here. Okay, and it's getting directed down into the pot here. And does it condense in there? Does it stay in? No, it'll just come bubbling back up and be in this area. Okay, so that's the problem. And the other thing is, remember those daughter product things I told you about? Some of them are solid, some of them are gas. And the gaseous parts are now starting to get released out here. Okay, so you've got all these daughter product thingies that are bouncing around here, and the steam is carrying some of the particle parts also. So that's coming down in here, and the gaseous stuff is bubbling back up, and it's coming in here. So this whole thing is getting full of hydrogen and these radioactive particles that are supposed to stay inside the core. Okay, next. All right, getting hotter, and more of these particulates are accumulating here. The guys in the control room, and I'll tell you what they were going through in a minute, but they're seeing not only is this pressure going up in pressure, but now the light bulb is going up in pressure. You got to do something, otherwise it's going to bust. Okay, go on. So they open up a vent from the light bulb, and they vented up into this space up here. Now that space up above is, again, where I spent much of my last month. It's a big old open area that has the machinery for moving the fuel around that we saw in those pictures. Nothing else much up there other than the spent fuel pool is open to that. But now they've released all this gaseous stuff, which includes hydrogen and the radioactive particles. And it's all up in that area, okay? So, you release hydrogen up into an area that's got oxygen, wow, bammo, you get an explosive mixture. Okay, so this is what everybody saw on TV, and this was the result, and we got some, if you want to look later on, I got some pictures up here. I actually flew some drones over the top and could look down inside. Now, anybody tell me what didn't explode here? The core didn't explode. The vessel didn't explode. The primary containment light bulb didn't explode. It was this big open area up top that exploded. Okay? A bunch of junk fell down inside. There's stuff that fell into the spent fuel pool. Not a good situation, but that core is still inside of the vessel, which is still inside of the containment structure. We just have this, we have a vent here. Okay? Again, not good, but this is remaining largely intact. Okay. There was some thought about one of the units, unit number 2, they thought that the little donut thing had ruptured, and from this presentation that I got a little while ago, that was still the operating thought. Recently, in the last couple of weeks, they actually sent a robot into this area, and it went all the way around the donut there and found that it was fully intact. Okay, so they're trying to explain why there was a big noise there, but there were explosions going on next door, so that's probably what they were hearing. So if you hear that one of the vessels or one of the containment structures ruptured, that is not true. Okay, so this did not happen. All right, next. All right, eventually they did manage to get power back, and they brought in fire trucks. They brought in all kinds of things and pumped in seawater and managed to get the pressure down and get water back in. So that's the current state now. Is it has been recovered and it has been cooled, and the operators do believe that they've got things under control now. All right. This is just kind of a timeline showing the 3 operating units, how long it took for loss of power. It all happened about the same time. Core damage started in Unit 1 at 4 hours, Unit 2 77 hours, Unit 3 42 hours. They all had their own reasons why it took much longer in some than others. Okay, fire pumps came in with fresh water at 15 hours here, 43 hours there. Again, just a matter of how you got in there and what you could do. Okay, hydrogen explosion happened at these different times. Off-site electrical supply came back anywhere from 11 to 15 days. So they lived without electric power for darn near 2 weeks. Okay? You also have heard that spent fuel pool, again, that's up at the top there, that there was damage up there, and that's also something that they found now is not the case. Fuel pool water levels never drop below the top of the fuel in the spent fuel pool. Again, the fuel's still hot. You have to keep it cool, so you got to keep water on it. And in fact, thanks to things like fire trucks and all, and having the lid blown off, they were able to keep water over that large spent fuel pool. So no significant fuel damage really occurred, and there may have been some when the roof caved in. Okay, it may have been damaged by impact, but not by overheating. All right, so again, this is what the plant looked like pre-tsunami, and this is what it looked like after. Okay, there's unit 1 over here, 2, 3, and 4. We don't talk about 5 and 6. Remember, in the other one, it was up the hill ways. It's slightly higher, still below, or still got impacted by the tsunami, but one of the diesel generators that provide the on-site power managed to survive, and they were able to hook that up to units 5 and 6, which were separated up the hill, and they were able to limp along. Okay, so those units, those survived without any significant damage. All right, I told you about getting water into a spent fuel pool. Well, here you've got the lid blown off of the reactor building, that big open area up at the top, and here's a fire truck squirting water up there. All right, so they're just dumping water in any old way you can. They also had cement pumpers. You know, if you ever wonder how you get cement up in a real high area, they've got pumper trucks that will pump that stuff up, and that's what they used here as well. What they're doing now is they're building a sarcophagus around it. Okay, they're actually they built this structure around each of the damaged units. Go ahead. And they're putting up these panels. You can see them lifting it into place here, and they're actually enclosing it so it's not open to the environment any longer. Okay, so you can see here it's almost done. They're putting a lid on it as well. All right, this is the control room for 2 of the units. Units 1 and 2, units 3 and 4, 5 and 6 share common control rooms. So then there's one operating unit controlled on this side and another on that side. This was right after they managed to restore light to the control room. A few minutes before this picture was taken, it was all dark. Okay, this other unit still is in the dark. All right, so you can imagine that you are the plant operator. Okay, there's dozens of operators, but the control room operator, the guy with this, the team of people that are in charge of keeping things running and keeping that core covered, they're in here and all lights are out. All you have is some emergency lights, and those don't last long either. And they're wondering, what do we do? All right, you can see here what happened to the light panels from the earthquake. All right, they're all down, and so now these guys now lights are back. So they managed to restore that, which is pretty simple compared to, see, each one of these things all needs power too. Okay, how do you get power to all those things? Well, these guys are trying to figure out what's going on out there. What do we do next? Okay, you're there minding your own business, an earthquake happens. Bam, what do you do now? Okay, you just lost all off-site power. Okay, everything's stable. Look, we just lost everything. Now what? Well, you want to pull out your manual and see what's going on? They didn't have a manual that said what to do. Okay, so here you are, and if you can see in here, here's a guy looking at a panel, and he's got those little pit helmet things on there. Here's a guy reading drawings by flashlight. Over here, I thought this was interesting. In order to get some instrumentation working, they needed battery power. Okay, all station batteries are underwater. All right, where else in the plant environment will you find a battery?
Parking lot.
Parking lot. They went out to the parking lot and pulled everybody's battery and strung them all together. Okay, that's what they are. You got to do what you got to do. Okay, next, sorry, this is like Apollo 13. Oh, if you can go back. This is an interesting quote here from somebody's testimony from the control room. When the power source failed, we felt completely helpless. Heated discussion broke out among the operators regarding whether it was important to remain in the control room without power and lights. I bowed to ask them to remain here, and somehow they agreed. Okay. So they had a duty. These are, I told you about the robot that went around the donut suppression chamber. These are guys operating robots. They were sending these robot things all over the place because you can't get to most of the plant. All right, releases. Who was here 3 Mile Island accident? Okay. Not a pleasant time. All right. Well, there were releases from 3 Mile Island, and don't worry about the units, but 481,000 terabecquerels. Okay. Fukushima, four damaged units, 630,000. Chernobyl, 5,200,000. Okay, so if we put it in a little bit of perspective. Okay, yeah, a bit more than 3 Mile Island. Anything that really happened from 3 Mile Island, health-wise? No, not really. So this is maybe 20% more or so, but not dramatically higher. Okay, and you saw the guy with the boots on. All right. You and I and everybody across the fruited plain get approximately 3.1 millisievert, whatever that unit means, of radiation just from living. Okay, if you live in Denver, you might have 5. If you live in Rhode Island, you might have 2. Okay, it depends a lot on where you live and
Your basement is like here.
yeah. Well, and yeah, if you live in the Reading Prong, you may be 10. Okay, but it's highly variable, but we all live with it. Okay, so they checked 10,000 people living near the Fukushima plant, and more than half of them got less than 1 out of the whole deal. 4,000 some got between 1 and 10, and a few got a bit more, but still nothing really dramatic as far as exposure to the general public. Okay? So, what are the consequences? 0.002% increased risk of cancer. 0.001% increased risk of death from cancer as a result of these releases. Okay? So, after all that, other than Chernobyl, I can't think of a worser thing to do to a nuclear plant. After all that, here's our total consequence. Okay, and of course we have to express it in terms of percent of risk because you never know. Okay, if you have 10,000 people, you might be one person out of that 10,000 people that succumbs to cancer because of it. There's no way of knowing because there's potentially a great many of them, so you're just increasing the odds, right? Biggest risk of health risk is obviously the psychological trauma and evacuation, and you're months away from home. Okay, this is really devastating to most of the people. There are vast areas that are not inhabitable right now. You can't go back. There are some areas that they're letting people come back. There are some areas that you can't. A large part of why there was so little exposure was they did have time to evacuate. And if you can imagine, you're dealing with a tsunami, in the aftermath of a tsunami, and you've got to get all these people out. Okay, and they were able to do it. All right, so what's happened in Japan? Well, again, you remember that map I showed you with all the nuclear plants? Last October, there were 10 operating units. The other day when I made up this slide, there was one. News is tomorrow, that one's shutting down. They will have 0 operating nuclear plants in Japan. Okay. It's hard to fault them, but they're not tearing them down yet. So, give them a little time. They have to make it up with natural gas and oil. All right, so they have to deal with that. Okay. Well, what about Germany? Hey, they're phasing out all 17 nuclear reactors by 2022. They're replacing them with windmills. Come on. Windmills. We're spending $79 billion. Switzerland, they said, we don't want to build anymore. Okay, fine, and they're going to phase out the existing ones when their operating lives run out. Okay, that's a couple of years away. France is an interesting story. They're going to continue operating. They've got 58 nuclear plants and 2 under construction. They just had a presidential election, first round. They had a Greens candidate that made a big deal about shutting down all nuclear. Okay, Eva Joly. She wanted them all shut down, and she was all over the news. She got 2.3% of the vote. Okay. The other 2 candidates, the Christian Democrat and Socialist, both of them are pro-nuclear. Okay, so even if the Socialist gets in, they stay in lots of jobs. Okay. Here in the USA, we're continuing to operate. Okay. They've actually licensed first new plant construction in 30 years. Vogel plant down in Georgia. Doesn't mean it's going to get built, but they're starting today. The environmentalists still have something to say. The industry and regulators, we're working together. Okay, everybody recognizes, okay, something's got to change. There's some design things that we can do that I'll be involved with, and there's things that the operators, lessons learned. Okay, and there's a lot of good things that are going to come out of it. Just like after 3 Mile Island, the plants are vastly better after that. All right, so you ask your average environmentalist, oh, no nuclear, no nuclear. Okay, nuclear generated electricity avoids almost 650 million metric tons of carbon dioxide per year in the U.S. If carbon dioxide is going to kill us all and the polar bears, why are we doing this? Why not? Okay, if they were really serious about shutting down CO2 emissions, windmills are not going to cut it, I'm sorry. Solar panels, you can shine that light on a solar panel for a while and generate some electricity with it. That'll help, right? But unless you all want to go to bed with the chickens, solar is not going to help you much. Okay? The EPA has a target for reducing carbon emissions. If they want to do that, if they want to meet it, they're going to need to double total nuclear capacity by 2050. And these plants, we're extending their lives. Right now, we've got a 60-year lifespan of most of our plants. And if we don't extend them any further, then we're going to need another 180 nuclear reactors to replace those and to displace the evil carbon. Okay. Again, I mentioned our plants are very safe. We have what we call a defense in depth philosophy. I showed you the multiple barriers. You got the pellet that contains those little nasty fission products. You've got the tube that they're in. You've got the water around it. You've got the reactor vessel itself. You've got the containment structure, so we've got all those different barriers there between the core and the environment. Okay, and we are analyzed for what we call blackout events, no AC power. Okay, there's no way that we can live as long as they did without having some of the same effects, but we have a coping strategy for a number of hours, and that's one thing that's going to certainly change. We're going to have to extend that. So we're going to mean a football stadium full of batteries, I don't know. Okay, so one of the things that we're doing right now is doing some new inspections, new rules for coping with blackouts, emergency procedures. I'm part of an emergency plan that if something should happen at the Susquehanna plant, my pager here is going to go off and I'm out of here and I'm going up to the emergency response facility. New reliable and filtered vents and some new instrumentation to help us, again, cope with the events as they're happening under these stressful situations. And there's long-term fixes to come. They're still working it out. So this is the Susquehanna plant up near Berwick. All right, see where the river is? Look, come back here. There's the river down here. See the plant up there? Is that the original site for the plant? Originally, it was going to be right down here. Okay, it's going to be right along the river because that's where the water is, right? Well, next. Who remembers Hurricane Agnes? Anybody here? Do that? Well, plant was still in the planning stage, and it put that site under several feet of water. Okay? And if we had put our diesels down there, yep, we would have lost the diesels and the fuel tanks and everything else. So Agnes comes along, they said, hey, look, we got this hill up here. So they put it up on top of the hill, and it's worked fine. All right, last summer, flooding on the Missouri River. Fort Calhoun plant, look at this. One next. Okay, here's the river, here's the plant. Surrounded by water. It came darn close to flooding itself. This was right here in Nebraska. Okay, one of the next. All right, so this plant was operating on its emergency diesels. It operated on those diesels for months. All right, so yeah, it's something we've got to look at. All right, something we've got to deal with. So the tsunami consequence. As of last October, the count was about 16,000 people confirmed dead, 4,000 missing, so call it 20,000 people. 500,000 residences are damaged or destroyed. 4 million homes lost electricity, and total area inundated by a tsunami was about 217 square miles. You're operating this nuclear plant, you're in the control room, and your family's out there. Okay? These guys are having the argument over whether to stay inside or not. But, you know, here's their family. They're outside. Okay? So we got to keep this in mind. All right? Everybody seems to have forgotten about the tsunami itself that actually caused the damage and the deaths. And, okay, so you just see the eyes of these people, you know, what else? What's next? So what can we do? All right. Well, yeah, we need to protect from tsunamis if you're in Japan, if you're on the coast of the U.S. There's plants on the east coast of the U.S. They're not immune. You know, the best way to build something better is to have a prosperous economy. All right, not by dragging us down, and by having reliable, safe energy. That's the way that we progress. And the more we progress, the safer we are. Okay, so we need the freedom, and you need, obviously you need appropriate regulation, appropriate government involvement, but yeah, we need to be able to, again, do what we can, and anyway, I think there's a great future for nuclear in this country, and I think that's it. Yep. All right. Anybody got questions? Donna.
Do you happen to know how many millisieverts of radiation one gets from an X-ray or a CAT scan?
I don't have that right with me, but I mean that's something that's easily found online. You know, they've got numbers for transcontinental flights, and from.
But it's probably higher than what even those who were exposed to the most.
Yeah, yeah. CAT scans are pretty hefty doses. They'll. You can get that, and you know, anybody gets a dental X-ray, what do? Put a big old heavy apron on.
So chances are very good that in the course of our everyday lives, we're exposed to more radiation than was exposed during what could have been a catastrophic event. It seems to me that this story is an example of how all of the safety protocols work, and work really well, even under catastrophic circumstances.
Right. Yeah. The critical thing is to keep things in perspective. Okay. It may have been higher. Certainly, you know, certainly messed up the area. Certainly caused dramatic disruption of lives and a lot of treasure and all that. But worldwide cataclysm, no.
The tsunami did that. The power
Right.
plant didn't do that.
Yeah. Well, the tsunami. Got to be clear. The tsunami did initiate the event, but the consequence, I didn't put it up here, but I've seen maps of the areas that you can't go back to now, and it's, it's a lot of area. So there's a lot of people's lives that are disrupted, and, but yeah, no physical medical emergencies that, okay. Yes?
You just mentioned the areas they can't go back to. Is that solely because of the nuclear issue, or is that because of the tsunami devastation also?
No, there are areas that have these fission products, the daughter products that escaped and are deposited in the soil and all over buildings and things. Yeah, you're not going to be able to go back there for some time. Same thing is happening in Chernobyl. Okay, there's, that whole Pripyat area can't get there. Yeah, right.
I guess one of the things that I always relate this to is that everybody goes back to that crazy movie China Syndrome. And the key is that is an out-of-control reactor where the reactor didn't scram. The way these reactors are designed, the control rods drop down, gravity has to stop working for the control rods not to scram. And when anything catastrophic happens, there's an automated system there. And I think, I just remember designing a 3 Mile Island. Literally, there's an axe with a cable to the power to the thing, I think, there, where if all else fails, the guys in the control room can cut that power cable that holds the control rod. The difference is Chernobyl and our lovely Russian designers, they put the control rods underneath, so they literally have to mechanically push the control rods up. Well, that's what happened, that's when it got all out of whack.
The Chernobyl reactor design is actually a plutonium weapons production design that was upscaled to produce power. And it's not a stable design. That's what happened there.
There's
Yeah.
next to no
If I
safety on
understand
it.
you correctly, the damaged plants now are completely enclosed, and is there a period of time where there will be enough decay or whatever that they will no longer be radioactive?
There is going to be a 10 to 20 year cleanup. Yeah, Chernobyl happened in 1986.
Yeah.
It's
So eventually
they're
then-
building a new
Eventually
enclosure
they will
around
be
that.
able to take down the structures altogether.
Eventually,
Yeah.
yes, but not for some time.
Yeah, it'll be some time.
It takes, yeah.
Is nuclear power in Japan pretty much dead or still under debate or?
Well, again, they've chosen to, keep the units that are shut down, and they're not restarting. There's discussions going on. It's not that it's dead, but I think you can still understand that they want to do some careful consideration before starting up again. So again, those plants are still going to be there. They're still perfectly good. They're maintaining them, and when they need to, I'm sure if they choose to, they'll start them up again.
And follow-up
Yeah.
question, in relation to Susquehanna, has it going to cost a lot of money to retrofit to include the lessons learned from Fukushima?
Well, it depends on what they're going to be, but like I said, the things like how much is it going to cost? The question is it going to be an expensive process? It's relative, but yeah, there's going to be a lot of things that need to be done. And again, we haven't settled on what the long-term fixes are. Things like adding additional battery capacity is going to be one thing, and we may need a new building to hold the batteries. So, so everybody get their volts and drive up to the plant. Right? We'll just back them up. You got a question here?
Well, how much contamination, was there in the ocean and all the surrounding areas?
There is contamination in the ocean. They did find that there was some contaminated water that was leaking out through one of the buildings, and they found the cracks in the concrete outside, and it was kind of going underground. And so the little harbor area there had some contamination, and they blocked that after a few days. So There is some in the ocean. The ocean is very forgiving. Ocean contains a lot of radioactive elements itself. But yes, there is contamination there and in the surrounding areas.
Does this extend to Alaska?
No, it's, there's two things that keep it from being a major issue that far away. For one, there's dispersion. Okay, so the concentrated releases wind up getting spread all over the ocean. And most of this stuff does get absorbed into the water pretty readily. And the time it takes to get there, things do decay with time as well. So they become less radioactive with time.
It was my understanding that the coral easily absorbs radiation and it doesn't let it go.
Coral is calcium based, and there are elements that would get incorporated into coral if it did get to it. Yes?
Just as a general note, when you were talking about containment of the buildings and so forth, for those who are interested, if you go online and look at the new containment that they're doing for Chernobyl, that is a really interesting engineering project that they're doing. It's pretty fascinating.
Yeah. Yes.
Recently, about 2 months ago, I got an email from a friend of mine that said, Nagasaki and Detroit, 70 years after we dropped the bomb. And showed that famous picture of Nagasaki where there's a single person standing amongst all the buildings, or what was buildings. It shows Nagasaki today, it looks like Dorney Park all lit up. Gigantic Ferris wheel, the whole place is just lit up. While Detroit looks like it just went through a bomb, buildings all, you know, what was once a vibrant city back during World War II.
Right.
Looks more like they dropped the bomb.
Yeah, well,
in Detroit
I
right
grew up
now.
with
So, I don't know what the big deal is with the, you know, we put a ton of radioactive stuff all over that area, and now there's just millions of people living right on top of it, so it can't be dying from what this little bit of stuff you just showed us.
Right. Well, again, there's difference in where it's spread and what's out there. There's different things that are out there that weren't there at the bomb sites. Okay, so there's a difference in some degree. Yes.
When this was all going down, we all learned on the news that there were people in the control rooms that stayed there, and we were all given the impression that they were under a death sentence. How many of those people actually died from radiation?
None.
If any? None.
No one has died.
Nobody has died.
Yeah, there are two control room operators got the highest dose of anybody, and they're actually within the limits, you know, that the Nuclear Regulatory Commission sets limits for a lifetime dose for nuclear workers like me. And it's roughly 5 times your age minus 18. And, you know, so that's just kind of the rule of thumb. And they're less than that. I haven't seen the ages of these guys, but if they're over 40, they're probably okay.
Just to follow up on that, the 2 people you showed getting 7 times the average annual dose that we all get were those 2 people. So they got 7 times.
What I showed
the
was the
average
public.
annual
It
dose.
was the public
That was the
outside.
public, not the
Yeah.
2
Yeah, it's
operators
not the
from
guys
inside? So they got much more than that, those 2 people?
Yeah, the people inside, they naturally did get more, but there's a whole crew of people whose job is to monitor how much dose, how much radiation absorption you get. Again, when I was in there, I got some. Yes?
The Chernobyl failure, was that a containment rupture then? It actually got that?
No, that was a runaway nuclear reaction that wound up causing not a nuclear explosion, but a steam explosion. So the water around the fuel itself got so hot that it caused the water, instead of boiling, it flashed on a big scale. And it blew the lid off. They had a concrete lid over the top, and it blew that concrete lid right off.
The containment vessels?
Yeah, and it instead of water around the core, they have carbon. So you have hot carbon exposed to air. Guess what happens? It starts burning, okay? And so you have a nice plume hot radioactive carbon going up into the stratosphere. Yes?
I saw these guys in these uniforms that look like paper. Is that what they wear to protect themselves from radiation?
Tyvek
Those
suits.
are, I wear the same thing. It's anti-contamination. Okay, it doesn't block radiation coming in. If you have an X-ray and you're wearing that suit, it'll go right through it. But what it does is keeps the crud that's laying all around you. Again, especially here, there's stuff everywhere. And if you brush up against it and you get it on your skin, you got to get it scrubbed off. Well, you just wear these coveralls, including a hood, including face mask. You don't want to inhale it. So you saw that one picture with the guys running the robots. They're wearing face mask breathing filters.
Because I see something on TV that they had uniforms that completely block. That they just did not-
Yeah, there's people marketing stuff and making money. Yeah.
Another comment is that
Uh,
how much did we get from when they were testing the bombs in Nevada? Probably, everybody worried about the nuclear plants, look at that.
Yeah, there was dose around the world from that.
The other thing people I don't think understand is that the radioactive material is some of the heaviest elements out there. So a lot, other than when there's an explosion of some sort, most of the stuff drops to the ground pretty quick.
Yeah, a lot of it does do that. There's some of those daughter products are gases. They're if you go back to your high school chemistry, you remember the stuff all the way over on the right on the periodic table are the noble gases, xenon, krypton, all those fancy stuff. There's radioactive elements of that, and they don't stick to anything. They just go into the air. Okay, so there is that stuff. And there's other things like radioactive iodine. Okay, you hear about people getting iodine tablets. Well, one of the key markers of things that would escape from a broken core is iodine, and it's at room temperature. It's a gas, so it'll float around through the air, and if you inhale it, it's going to concentrate in your thyroid, right? And so if you inhale it, you get it in your thyroid, you get thyroid cancer. So that's why they pass out to people that are potentially exposed to it iodine tablets, because then you overload your thyroid with iodine, can't absorb anymore. So if you do inhale it, you just excrete it right back out. Okay, so that's what it is. It doesn't protect you. Okay, one more?
One more.
Yeah, I had a friend of mine who worked over as a missionary in the Ukraine with the children from Chernobyl,
Yeah.
who all had cancer. And there was one doctor there who really worked with these kids, but that you showed the amount of radiation that was released from that Chernobyl nuclear. What do you know about it?
About the
Chernobyl.
Chernobyl, the radiation.
Children and the, yeah.
Oh yeah. Well, actually, if you look at what was the highest number of deaths from Chernobyl, it was the women who were panicked into having abortions. After Chernobyl, there was an epidemic of women having abortions to eliminate these children that could potentially have been exposed. Well, I know there's a lot of children that were exposed that have very serious consequences, but the women who were pregnant at the time, you are the most sensitive at that time, but there was no reason to have done that with the unborn. That was easily the largest loss of life from that. But yeah, I agree. There were it's part of the problem living in that society was they wound up exposing all these people to something totally unnecessarily. All right, thank you.
Thank you.
Thank you,
David, that was very good. Boy, give you a lot to think about. 2 items yet.